So, we have been looking at forced vibration analysis of one dimensional structures in the past few lectures. Today, we are going to look at we are going to continue our discussions on forced vibration. In the previous lectures, we have seen harmonic forcing, systems with harmonic forcing, which we have separated in space and time. There is a distribution function for the force, and then there is a multiplying harmonic function of time. Today, we are going to look at general forcing, which means forcing which need not necessarily be separable in space and time. So, we are going to look at general forcing in today's lecture. Now, let us consider some examples of this general forcing. So, in one of the previous lectures, you have already seen that an initial value problem of with certain boundary conditions and initial conditions So, an initial value problem can be equivalently stated as So, these two statements are equivalent. So, essentially we have converted an initial value problem to a forced vibration problem. Here this is the Dirac delta function, and this is the time derivative of the Dirac delta function at t equal to 0. So, this problem is a forced vibration problem, which is equivalent to this initial value problem. So, in this case, as you can see, this kind of forcing is a very special, is in a very special form, and this is not a harmonic forcing. So, forcing of this type, or when a force is traveling on a string, for example, on a bridge you have a car traveling at a certain speed. So, you have a traveling load problem or traveling mass problem. So, such forces load the structure and they are not harmonic forcing. In fact, in such problems space and time are coupled, they are not separable, as we will presently see in this lecture. So, problems of this type can be considered to be of general forcing. I mean, these are problems with general forcing. So, let us look at how do we solve a general forcing problem. So, we consider, for example, so let me state the problem. So, we have the equation of the differential equation of motion with of course, certain boundary conditions. So, this q x comma t is a general there is a general form of the force which which we are now considering. Now, to solve or approach such problems, we have various methods. What we are going to consider here today are the modal expansion method. We are going to concentrate on this modal expansion method, and towards the end we are also going to look at the Green's function method. So, essentially today we are going to look at these two methods. So, let us start with this modal expansion method. We have discussed in an initial in a previous lecture how or why this modal expansion technique works. It is because the modal space is a forms a, or the eigen functions of the eigenvalue problem of a system form a complete basis, which means any shape of or any configuration of the system can be represented by these eigen functions. So, this is the basis of this modal expansion technique. So, we are going to look at this problem with certain boundary conditions. And as we have discussed, the solution we will represent in this form. So, these are the eigen functions of the corresponding eigenvalue problem. Now, when we substitute this in the equation of motion, so these eigen functions already satisfy these boundary conditions. So, we need not worry about the boundary conditions. So, here we now have to determine these coefficients, so that this expansion satisfies the equation of motion. So, we have substituted this expansion in the equation of motion, and now here this k is a linear differential operator, and therefore, what we can do is we can commute this summation and the operator and we can rewrite this equation in this form. Now, recall that the eigenvalue problem for this system So, this was the statement of the eigenvalue problem. So, here the differential equation of the eigenvalue problem, from here we can see this expression of the stiffness operator operating on the eigenfunction. So, we can replace it from here, and then what we obtain we obtain this. Now, if I use the orthogonality condition, so I take the inner product So, what I do is I multiply both sides of this equation with W j and integrate over the domain of the problem. So, then we know that from the orthogonality of these eigenfunctions, we already know that so if j is not equal to k, then this is 0. So, what this is going to do is filter out the jth coefficient in the expansion. So, we are going to get So, we are going to get the jth equation, and therefore, I can write this in this form, where this force term F j is given by so, and this I can take for different W j, and I can generate all these equations corresponding to the coordinates of the jth of the individual modes. So, I have these equations governing the coordinates of the system in the configuration space or the modal space, and that is a forced dynamics problem, where the forcing of the jth mode is expressed in this form. So, once we have the applied external force, we can easily compute this by performing this integrations. Now, this is a second order ordinary differential equation. So, we will need two initial conditions for this problem to solve the problem completely. So, what we need are the initial conditions. Now, we are given these initial conditions on the field variable. So, we once again have this expansion and similarly from the velocity initial conditions, we get this equation. So, we have to solve this this equation with initial conditions on p at 0 and p dot at 0, which we are going to now solve from these two equations. So, once again if we use the inner product, now here remember that this is the orthogonality condition. Therefore, what we must do to solve these coefficients in a straightforward manner. So, what we do is we multiply both sides with mu and W j and integrate over the domain of the problem. Once we do that, is going to filter out the jth term in this expansion, and therefore, so that is how we can solve P j 0, and we can obtain all these infinitely many initial condition on the modal coordinate. Similarly, we can also find out the initial velocity condition So, once we have all these initial conditions P and P dot, then we can solve this problem. So, once we have these initial conditions, then we can very easily solve. So, we know already know the solution of this kind of forced dynamics. Now, here there is one thing to note, that what we have achieved in this process is the discretized equations of motion. So, we have discretized the force vibration problem. Now, let us look at some examples. So, the first example that we are going to consider is that of a force traveling on a string. So, let us look at this problem. So, we have a taut string on which there is a concentrated force which is travelling at a speed v. So, this F is a constant. So, let me write down the mathematical formulation of this problem. So, So, we have the string equation of motion with this forcing and of course, the boundary conditions So, these are the boundary conditions and there can be certain initial conditions. Now, here we will be looking at the forced problem. Using this expansion in terms of the eigenfunctions of the taut string. Now, if you substitute this in here and follow the procedure that we just now discussed, then for the jth mode the discretized equation of motion appears to be in this form, where this omega j so this is our equation of motion. Now, the solution of this equation can be easily written as so this is the solution of this equation provided V is not equal to C, where this C is the speed of transverse waves in the string. So, C is the speed of transverse waves in the string. So, as long as the velocity or the speed of travel of this force is different from C, is less than C, for example, this is going to be the solution. So, you see, when V equals C, and if you look at this omega j, then you will realize that when V equals C, this becomes a resonant forcing of the string in the jth mode and therefore, in all modes. So, all modes will be in resonance if V equals C. So, that would be a resonant forcing of the string, and the solution is, as you know already, is in a different form. So, So, this solution is valid as long as V is not equal to C. You can also find out the resonant solution using the standard techniques that you have studied in discrete vibration problem, in a course on discrete vibration. Now, so this is a solution form, therefore, here these are unknown coefficients which form the homogeneous solution of this system, which have to be found out from the initial conditions. So, we will consider a stationary string before the force starts traveling on the string. So, initial displacement is 0, initial velocity is 0, and if you solve for these coefficients, then you will see that the coefficients turn out to be and therefore, the final solution of our problem so, this is our final solution, and this solution is valid of course, when V is not equal to C. Not only that, but also time, the time interval for which the force is on the string. As soon as the force crosses the string, this solution is no longer valid. You have to solve for the string with certain initial conditions, which are the final conditions at t equal to L over V of this. So, you will get the final displacement of the string and the final velocity at t equal to L over V from this expression, that goes in as the initial conditions of the string in free vibration. So, that would be an initial value problem. So, after this you will have to solve an initial value problem to understand how the string behaves after the force has left the string. So, that is an initial value problem which you have to solve using the final conditions from this solution, and we have already seen how initial value problems are solved. Let us look at certain configurations of the string. So, here you will see at the configuration of the string at certain time instants. For example, here this is 0.2 L over V. So, this force has travelled 1/5 the total length of the string, and this is how the string looks like. You see that this portion of the string is as yet undisturbed, but when t reaches 0.4 L over V, so 40% of the distance has been covered. So, this information that there is a force travelling on the string has reached this end. Here at 0.6 L over V, you can see a kink forming here. So, actually the information is now reflecting back and forth on the string. Now, to and this shows at point L 0.8 L over V. Now, so these are snapshots. Here I have a simulation of or animation of the same thing. So, I have taken a number of terms in our expansion that I just now discussed, and I have plotted the shapes of the string at different time instants and prepared this animation. Now, here you can see that the string appears to move in a very strange manner. It looks very strange that it looks static. Certain portions of the string look static for certain time instants. So, what is happening is this disturbance which is created by this travelling force travels on the string as a wave, and it reflects back and forth on the string from the boundaries. Unless the disturbance reaches a portion of the string does not know that the force is travelling. So, it remains, it looks like static. Remember two things in this animation. One thing is that this is a slow motion of the actual thing that is happening. So, I mean it is very difficult to observe this kind of motion by naked eye. You have to record it and run it in slow motion. The second thing is this animation does not take care of the motion of the string after the force has left. This is just a repeat of that animation when the force is travelling on the string. So, here you do not see that initial value problem solution. Now, this is at low speed where V over C is 0.1. So, it is 10% of the critical speed. In this animation, this is a near resonance. So, 0.95 V over C is 0.95. So, it is 95% the critical speed. Here you will find that those reflections of the kinks etc., they are not so easily observable, at least. And the amplitude is growing as the force moves from left to right, which is a typical behavior of a near resonant solution. So, at resonance, as you know, that the amplitude grows linearly with time. So, this is near resonance, slightly lower. So, you can see the behavior of the string, which is it is distinctly different from the previous behavior. So, these motions, this is a transient motion, and this has to be understood in terms of the propagation of waves in the string, which we are going to take up later in this course. Now, so we have looked at the modal expansion solution. There is another method which we are going to now look at briefly. We have already come across this Green's function method in our previous lecture. So, what we are going to solve is So, in the Green's function method, we solve a problem of this type, where the forcing has a very special form. These are Dirac delta functions, or Dirac delta distributions. So, the forcing is of a very special form like this. So, what in effect this represents is, it represents an impulsive loading at the location x equal to x bar and time t equal to t bar. So, we give an impulsive loading at the location x equal to x bar on the system and time t equal at time t equal to t bar, and we are going to look at the solution of the system to such a loading. And here the boundary conditions are homogeneous and initial conditions are all 0. The solution of this system is known as the Green's function. We will represent this in this form. So, these points are important, that we have homogeneous boundary conditions and 0 initial conditions. So, always this Green's function is calculated with these conditions. So, this will be tacitly assumed whenever Green's function is calculated. So, homogeneous boundary conditions, 0 initial conditions, and we know, we have seen in a previous lecture how non-homogeneous boundary conditions can be converted to homogeneous boundary conditions. So, if required, we have to do that and then calculate the Green's function. So, why? Let us first look why Green's this or how this Green's function method works. So, we claim that for any arbitrary forcing, when we have forcing in the form of q x comma t, a general forcing, then the solution actually can be obtained in this form. So, once we have the Green's function, the solution to an arbitrary forcing can be determined like this. So, let us see why this happens or how this is happening. So, let me write this this differential equation. Let me write this differential equation as so. This is our problem where P so I am representing this full operator using P. Now, what we do is we are actually solving this problem first. with of course, those homogeneous boundary conditions and 0 initial conditions. And then what I said was the solution is given by this. So, let me apply the operator P on this. Now, this integral is over x bar and t bar. So, this operator can go inside and it will operate only on g, and we know that P of g is and this is equal to therefore. So, therefore, this is definitely a solution of. So, W given by this argument is definitely a solution of this system. So, this shows that we can we have the solution W in terms of the Green's function. Now, let us calculate the Green's function for string. So, we are giving an impulsive loading at time t equal to t bar at a location x equal to x bar. And the solution is the Green's function, and we are considering homogeneous boundary conditions and 0 initial conditions. So, first what I will do is to determine this Green's function. So, we have to solve this Green's function now by solving this system, this problem. So, what we are going to do to simplify things is we will take the Laplace transform of this equation. So, we define the Laplace transform as follows, and we know that the Laplace transform of here this is 0 because the initial conditions are 0. Similarly, Laplace transform is given by this with 0 initial conditions. Now, once you take the Laplace transform of this equation, then and rearrange, we obtain this equation along with the boundary conditions like this. So, this is our boundary value problem that we need to solve now. Now, because of so this is so the homogeneous, we have homogeneous boundary conditions. So, therefore, we can look for solutions in this form. So, substituting this in the boundary value problem, and when we rearrange, take the inner product on both sides with sin n pi x over L. So, we substitute and take inner product, so we substitute this in the differential equation and take inner product with sin n pi x over L on both sides, and then it filters out the nth coefficient, which I can write, and this can be done very easily. So, we will obtain this coefficient, and finally, the solution therefore, is obtained now. This so, this is the solution in the Laplace domain. Now, we have to take inverse Laplace transform, which can be done by residue theorem, and the final solution. These are simple steps. I will write the final solution. Here this is the Heaviside step, which comes from the causality, which means that the solution does not exist before the impulse is provided. So, t less than t bar is 0, the solution is 0. So, the solution is non-zero only when t is greater than t bar. So, this is your solution of the Green's function, and as I have discussed, for any arbitrary forcing you can determine the solution using this integral. So, this is a very powerful method of approaching forced vibration problems with arbitrary forcing. Now, you can so we know how to solve the Green's function method. Here we have used the modal expansion technique to solve the boundary value problem. In a previous lecture we have seen how the Green's function was solved in a different method. So, this approach gives us a very powerful method of solving forced vibration problem of continuous systems. Now, in this lecture we have considered the general forcing of one dimensional continuous systems, and we have looked at the modal expansion technique and the Green's function technique for solving the forced vibration problem of one dimensional systems. So, with that we conclude this lecture.